Hello everybody, thank you so much for joining me here today. In today's video, we are going to be talking about circles and inscribed angles. We're going to be talking about the theorems that arrive with inscribed angles within circles, and then we're going to be tackling some practice problems. So with that, let's dive straight into it. First of all, let's talk a little bit about what a circle is and how it is constructed. So by definition, a circle is a shape such that you have a center point and you have some radius, and your radius, we'll call it r, is a uniform distance from your center point. So imagine if you have like a string and a thumbtack. If you place your thumbtack and pull your string taut and then rotate your string 360 degrees until you come back to your starting position, then you will have done one revolution and you will have created a circle. Okay, from that definition, we understand that our central arc or our central angle measure here, we'll call it theta, is equivalent to the distance that you traveled in your arc measure. So our angle theta is equivalent to this arc measure. Okay, so this is a key insight in understanding your central angle and your arc measure. So your central angle is congruent to your arc measure. Okay, excellent. So moving forward, let's draw in a central angle. Now, a question you might have or might be curious of is there a relationship between a central angle and an inscribed angle? And an inscribed angle is simply an angle which comes from your circumference rather than the center, but it covers the same arc measure as your central angle. So our question is there a relationship between our central angle here and the inscribed angle here? That's what we're curious about. So let's see if we can find some sort of relationship. So let me draw in a radius from our center. And notice that with this dotted line, with this radius, we've just created two isosceles triangles, okay? And that's because all radius, by the definition of a circle, are congruent. Therefore, this line is equivalent to this purple line, which is equivalent to this other purple line. Therefore, by definition of isosceles triangle, this angle is congruent to this angle. And similarly, this green angle is congruent to this full angle here. So notice that this green angle overlaps with that blue angle. Also notice that our inscribed angle is defined by our green angle minus that blue angle. Okay. Also notice, how can we define our central angle? Well, our central angle is made up of the third full angle in this super skinny isosceles triangle. So this red angle, which I just marked, could be defined as 180 degrees minus my two blue angles. And then the third angle in my larger isosceles triangle, the one with the two green angles, would cover this bit. So that's to show that my central angle is equal to my red angle minus my purple angle And my purple angle is, of course, 180 degrees minus my 2 green angles. So if I plug in what my red angle is and what my purple angle is into my central angle, then what will I have? Well, I'll have that my central angle is my red angle, which is 180 minus 2 of my blue angles. And then I will subtract my purple angle minus my purple angle, which is 180 minus my 2 green angles. Okay, so if I simplify, what do I have? I have 180 minus 180, which is of course 0. And then I have a minus 2 blue. I'm left with a minus 2 blue. And then a minus 2 green. So that's a plus 2 green. Now I'm going to shuffle this around a tiny bit. I'm going to put the green in front and factor out a 2. And I'm left with 2 times my green angle minus my blue angle. And this is my central angle. This is equivalent to my central angle. Now what we need to notice is that my inscribed angle up top is my green minus my blue angle. So my central angle is just twice my inscribed angle. So my central angle equals 2 times my inscribed angle. Fantastic, fantastic. So that is where this key relationship comes from. That is our angle at the center theorem, and it simply states that our central angle is double our inscribed angle. Fantastic. Now let's talk a little bit more about that. If we have some central angle, and let's call that central angle 2 theta, and then we have some inscribed angle, let's put it over here, just like we just had, we now know this angle measure to be theta. But what if we had a separate inscribed angle? Oops. What if we had a separate inscribed angle, like up here, for example? Well, we could draw similar isosceles triangles like we just did, and we would find that this would also be half of our central angle. So this would also be theta. And the key insight is it doesn't matter where our inscribed angle is, it will always be half of our central angle. Okay? So all of our inscribed angles are congruent, of course, as long as they are going to the same arc measure. Okay? They have to be going to the same arc measure, but all of the inscribed angles will be congruent. Let's think of one more special case. How would it be if we had some diameter? If we had some diameter and then some point on our circle, and we connected that point to both ends of our diameter and formed a triangle. What type of triangle is this? Well, pause the video and think about it. I'll give you a couple seconds. Okay, if you said a right triangle, then you are absolutely correct. And this is the angles at a semicircle theorem, also known as Thales theorem, but it stems from our angles at a center theorem, such that our central angle is this straight line, which we know to be 180 degrees. Therefore, our inscribed angle up top must be half of our central angle. Therefore, this is a 90-degree angle. And again, just to be clear, it does not matter where we draw our inscribed angle to be. If it goes to the same arc measure, then it will also be 90 degrees. And you can see that this is also a 90-degree angle. It does not matter. Fantastic, fantastic. Next up, something else that's interesting about inscribed angles comes whenever we are looking at cyclic quadrilaterals. Now, cyclic quadrilaterals is simply the fancy term for quadrilaterals which are inscribed in a circle. And we want to look for the relationship between angles in a cyclic quadrilateral. So, something I would like to point out is this angle here is an inscribed angle for this full arc measure. Okay? Therefore, if we drew in some additional radii, then if we called this angle theta, then this central angle must be 2 theta. And similarly, if we took this angle to be angle phi, then its arc measure, well here, notice that it's an inscribed angle for this arc measure in red. Therefore, the central angle would be 2 phi. Also notice that 2 phi plus 2 theta equals 360 degrees. And if we divide that by 2, we'll have theta plus phi is equal to 180 degrees. Therefore, opposite angles in a cyclic quadrilateral are supplementary. They add up to 180 degrees. Okay? As a quick recap, these were our 4 relationships we just talked about. We talked about, most importantly, this first one, and this is the angles at the center theorem. Then we talked about how all inscribed angles going to the same segment or same arc measure are congruent, and this is rightfully named the angles. Oops. Sorry about that. This is the angles at a shared segment theorem. We have this third example, which is the special case whenever we have a semicircle. And this is the angles at a semicircle theorem. It's also known as Thales theorem. And then lastly, we have this relationship between opposite angles in a cyclic quadrilateral. This isn't a theorem. This is just simply comes from the definition of a cyclic quadrilateral. Excellent, excellent. Now with all these theorems, let's solve some practice problems. Here in this question, I want you to tell me what is the value of x plus y. Here, I'll let you pause the video and see if you can solve this problem on your own. I'll give you a couple seconds. Okay, so for this problem, you need to draw in a radius to your other vertex, and then notice that you just created 2 isosceles triangles. Therefore, angle x, is going to be congruent to this skinny angle up here. And similarly, angle y will be congruent to this angle here. Therefore, we can see that our inscribed angle is equal to our blue plus our purple, and our inscribed angle is going to be half of our central angle, so it will be 25 degrees. Therefore, x plus y is also equal to 25 degrees. Fantastic. Here we have another problem. Again, we want to solve for x, so I'll give you a couple of seconds here. Feel free to pause the video. Okay, so I want you to pay attention to the arc measure in which our inscribed angle is looking at. And angle x is looking at this arc measure here. And also, this central angle is looking at that same arc measure. So if we can find the value of our central angle, we'll be able to find the value of our inscribed angle. Okay, notice how this long piece is a diameter and it's a straight line. So a diameter will have an angle measure of 180 degrees. Therefore, our central angle must be 60 degrees. Thus, our inscribed angle x must be half our central angle, so it is 30 degrees. Excellent. Onward. We are looking for the value of angle x. Let's just dive straight into this one. Here, angle x is looking at this arc measure. It's important to notice that angle 70 is an inscribed angle for this arc measure that I'm highlighting in blue. Therefore, if I draw in some central angle, I know this central angle to be 140 degrees. It will be double my inscribed angle. And also, I can find this other portion to be 40 degrees as it meets a diameter. And if this is 40 degrees, that means this arc measure will also be 40 degrees. Therefore, my inscribed angle x will be half of the arc measure. Thus, angle x is equal to 20 degrees. Fantastic. Here we have a cyclic quadrilateral. For this problem, I want you to tell me the relationship between the blue and the purple angle. Is one larger than the other? Are they equivalent? Are they supplementary? Or is there not enough information to tell any such relationship? Pause the video and I'll give you a couple of seconds. Okay. So recall that with cyclic quadrilaterals, the opposite angles are supplementary to one another. Therefore, if I look at this smaller circle, this angle here, this red angle plus the blue angle in question are supplementary, so they must sum to be 180 degrees. However, also notice that my red angle and my purple angle form a linear pair, and so they also equal 180 degrees. Therefore, I could subtract the red angle from both sides, and I can see that my blue angle is equal to my purple angle. So these two angles in question are equivalent. Fantastic, fantastic. Continuing forward, I have this problem. We are looking for the highlighted arc measure. This is probably the hardest problem in this group of problems, so I encourage you to pause the video and see if you can solve it on your own. Also, while you're pausing the video, be sure to hit that subscribe button. It truly helps and I truly appreciate it. Okay, with that, let us solve this problem. So, what can we gather from this picture? There's a lot of little things to get. we see that this angle 20 is an inscribed angle for this arc measure. Thus, this arc measure must be 40. We can find, here let me change the highlighting color. We can find this arc measure to be of 80 degrees as the inscribed angle is 40. Okay. And what else can we find? Well, also notice that we have a diameter here. And since we have a diameter here, we know that this last bit of arc measure, here I'll change color again, this arc measure must be equivalent to 60 degrees, as 60 plus 120 will be 180, which will be our full central angle for our diameter. And if this is 60 degrees, then this angle here must be 30 degrees. Now that's a little bit extra. We didn't actually need to say that that was 30 because now we have our full circle minus our x. Okay, we know a full circle to be 360 degrees. So we're going to take 360. We're going to subtract 120. Well, really, let's add these up. We're going to subtract 120 plus 60 is 180. 180 plus 40 is 220. And 220 plus 80 is 300. So we'll subtract 300 and be left with 60. Therefore, angle X is equal to 60 degrees. Excellent, excellent, excellent. Here we have one more problem. Again, it's a cyclic quadrilateral problem. So what do we know? We have three variables. Variable y is what we will solve for first because it's opposite the given angle. And we know 112 plus y must equal 180 degrees as opposite angles in cyclic quadrilaterals are supplementary. Therefore, angle y must be equivalent to 68 degrees, as 68 plus 112 is 180. Now, how could we find angle x and angle z? Well, I want you to notice that angle x is an inscribed angle for this full arc measure. And this full arc measure is given by 92 plus 88. And 92 plus 88 is 180 degrees. Therefore, x is half of 180. And so x will be equal to 90 degrees. And z is supplementary to angle x. And so z will also be 90 degrees. And there we have it. There is some practice problems using our inscribed angle theorems. I hope you enjoyed this video. I hope you learned a lot. Let me know down in the comments below. Again, hit that subscribe button, and I'll see you in the next video.